Hello and welcome to College Physics, Lecture 2, Mathematics Review, Part 2. In this lecture, we're going to just continue what we were discussing last time, but we're going to add in a lot of new topics. We're first going to look at direct and inverse relationships, then we'll look at the equation of a line. We'll follow that up with a brief discussion on areas and volumes of various geometric shapes. And then we'll conclude with plane geometry and trigonometric functions. So let's go ahead and jump right in. So we'll start with our direct relationships. So anytime you have two different variables, say x and y, and if they respond in the same way to one another, meaning if one value increases and as a result the other one increases, or if one decreases and the other decreases as a response, those are said to be in direct relationship, or more specifically, we say they are directly proportional to one another. If that is the case, we use a symbol to denote proportionality. We use this Greek symbol alpha. So this right here says y is proportional to x. So again, that means that as x increases, so does y, and vice versa. In an equation form, something like this would be given as y is equal to m times x, where m is just a random constant, any number. And so we have a graph on the right-hand side here of the equation y equals m times x. We don't know any specific values, but this is just a general trend. So notice the blue line, this is the equation of a line for y equals mx. Notice that as we move to the right, in other words, as our x value increases, well, we also move upward. So as we move higher and higher in x, we're also moving higher and higher in y. Thus, they are directly related. And vice versa, as you move to the left or downward in x, you are also moving downward in y. So these are said to be directly related or proportional to one another. Now, the equation that I've given here, y equals mx, this probably is looking fairly familiar to some people. It's hinting at a very specific equation that we'll get into in just a few moments. Well, this is what happens if your two variables directly relate, but they don't always do that. Sometimes, if you increase one variable, the other one will decrease in response. And so here is just an example. So if you have an inverse proportionality where one increases and the other decreases, you might write this as y is proportional to 1 divided by x. This shows inverse proportionality because as you increase your x value, that means you're dividing by more and more. And if you divide by more, that makes your y value smaller. So much like the previous example, we can put this into an equation form and say, for example, y is equal to k divided by x, where in this case, k is our constant, just like m was in our previous example. So here's an example of this as a graph. We have y equals k divided by x. And again, notice the inverse relationship here. As you increase in x, in other words, as you move to the right, your y value is actually going down. So x is increasing as you move to the right, but y is decreasing. These are said to be inversely related. So this kind of culminates in our discussion with the discussion of the equation of a line. And so I was mentioning that y equals mx probably looks familiar. Well, that's because the full equation of a line is y equals mx plus b. The one thing we were missing is what the y-intercept was. That is our b value. So there's a lot going on in this diagram, but what we've done here is we've chosen 2 points along our line, this yellow line here. So these blue dots are just representing 2 random points along the graph, or 2 what we call coordinates. Each coordinate has a specific x value and a specific y value. So I could say this is the point, I don't know, maybe 3, 4, for example. 3 over in x, maybe 4 up in y. There's no numbers, of course, I'm just making that up, but still. And then we have another point, so we'll call that the coordinate x2, y2. Now imagine traveling from our first to our second coordinate. Well, as we do that, both our x and our y values are changing. And so in physics, or in mathematics typically, we represent a change with the delta symbol, which is this giant triangle that you see. So when you see delta x, that is telling us the change in x. In other words, you're looking at the difference between your two x values, so x2 minus x1. And we have a change in y as we move from the first to the second point. So as we do this, we're moving upward, so clearly we're changing in y, so we will have a change or delta y value as well. So this is important because it relates to what that m value is in our equation. B is the y-intercept, which is just wherever your line crosses the y-intercept, crosses the y-axis. In the case of this line, it would actually be a negative value somewhere down here. But m is what we call the slope. Slope is just the name given to the steepness of a line. So this is why we need to bring up the discussion of delta x and delta y, because how steep your line is depends on how much you move in x and how much you move in y as you move from one point to the other along a graph. The simplest way to define slope, at least the way that I have learned it and like to use it, is we say rise over run. In other words, it's how much you've risen, so gone from y1 to y2, and how much you've run horizontally from the first x value to the second x value. So rise over run simply means the difference between your y values over the run, the difference in your x values. To simplify this, that's simply delta y over delta x. This defines our slope. So if you think about this, if you're not changing in x very much, but you're changing in y a lot, well, you're going to have a very steep slope. Your line is going to be angled very highly. But if you are moving horizontally a lot, but barely at all vertically in y, well, then you're going to have a really shallow slope. So these changes in x and y values dictates how steep our line is, or in other words, it dictates the slope. Now, in general, you can have 4 different kinds of slopes. A slope could be either positive, negative, 0, or undefined. In the case of a positive slope, what you have is a line that is going, as you might imagine it, uphill from when you go left to right. So anytime, it doesn't matter where the line is located, anytime you have a line that's pointing upward as you move left to right, that is considered to be positive. A negative slope is whenever the line points downward or downhill as you go from left to right. 0 slope, this one should be pretty straightforward. No slope means it's just a horizontal line. And whenever you have a perfectly vertical line, we call that an undefined slope. We say that it's undefined because slope is defined as change in y over change in x. Well, notice here in this example, we're not changing our x value at all. If I look closely at the numbers, it's negative 4 in the x value all the way through this. So we don't have a delta x, it's 0. Well, we should know that in mathematics, you cannot divide by 0. That is an undefined mathematical operation. So we consider that an undefined slope. Okay. From here, we're just going to kind of take a step into some easier things. We won't even go through some examples, but I'm just going to give you equations for the area and or volume of various shapes that we might encounter in our physics course. So we'll start pretty simple with a rectangle. A rectangle has 2 general dimensions, length and width. So if we wanted to find the area, which is a 2-dimensional term, we simply take the length times the width. So that's it. You can't find the volume of a 2-dimensional shape, so all we really need to know is that to get the area, it's just length times width. But let's take this rectangle and extend it into the 3rd dimension to create a box. So we still have a length and a width like we did in the first example, but now we're moving into the 3rd dimension with a height as well. If you wanted to find the total area of this entire object, in other words, the surface area, that is the entire area of the outer perimeter of this object, well, you have quite a bit of work ahead of you. Because a box like this is technically 6 rectangles. You have the front and the back, the left and the right, and the top and the bottom. So essentially you have to do this area 6 times. But you can simplify it a little bit if you recognize that, well, the front and the back are going to be the same dimensions, the left and the right sides are the same dimensions, and the top and the bottom are the same dimensions. So you have 2 length times widths for the top and the bottom, 2 length times height for the front and the back, and you have 2 width times height for the left and right sides of the object. I don't think we'll ever encounter having to do this in our class. It takes a bit of time, but just know it's basically just 6 operations of finding the area. Volume, which is a 3-dimensional term, is simply the length times width times height. So you just multiply those 3 values together. Another shape that we might commonly see in the course is a triangle. The triangle is defined typically by the base, B, and the height of the triangle, H. If you wanted to find the area of a triangle, it is 1/2 base times height. But wait, there's more. We will encounter circles. So a circle, if you wanted to find the area of it, we should probably know this one. It is pi r squared, where r is the radius, and in the image above, d is the diameter. Note, diameter is just 2 times the radius. Just for added information, I'm also going to throw in circumference, even though the title of the slide is areas and volumes. Occasionally, you will have to find the circumference of a circle as well, which is just 2 pi r. And note, the definition of circumference is the outer perimeter of the circle. So it's the length along the outside of your circle. Well, let's take this object and extend it into 3 dimensions as well, and we have a sphere. If you wanted to find the surface area of the sphere, that is 4 pi times the radius squared. And if you wanted to find the volume, how much space it takes up, that is 4/3 pi r cubed. Last but not least, a cylinder. We encounter cylinders more frequently in physics too, but regardless, we'll still encounter it maybe once or twice in our course. The area and the volume of these objects are quite interesting, I think. So let's say we want to find the surface area. Well, take note of the fact that a cylinder is basically 2 circles, the circle at the top and the circle at the bottom, and then this like barrel shape along the edges. So the area is simply 2 circles, and we said the area of a circle is pi r squared. Well, we have 2 circles, so 2 pi r squared. Right, so that's one part of our equation for the area, but we still have to figure out the area of this barrel shape in the middle. Well, the way I think of this one is, imagine looking at the circumference of this circle, 2 pi r. Now imagine taking that circle and physically moving it downward and tracing out that barrel shape. You're moving it downward along the length L. So you have the circumference 2 pi r along the entire length L until you get to the bottom. So that part of the area is 2 pi r, the circumference, times the length of the cylinder. Okay, you can also find the volume of this 3-dimensional shape. The volume, you can think of it in the exact same way. Take the area of your circle, so the full area, pi r squared, and move it down along the entire length of the cylinder. And that traces out the entire shape of this object. So it's the area along the length, so pi r squared times L. All right, we'll continue with a different form of geometry here. We're going to look at plane geometry. In other words, we're going to look at what angles are doing in various situations, let's just say. So here on the bottom, we have an image of 2 intersecting straight lines. anytime you have two lines that are intersecting, the angles on opposite sides will always be equal. So in the case of this image, angle A and angle C are exactly the same, but so are angles B and D. So again, opposite angles formed when you have two straight lines that intersect will always be equal. Well, there's several other situations that we might encounter where angles will be equal without being explicitly told. When you have two parallel lines, like you see at the top here, these two horizontal lines, that are then intersected by a diagonal line, angles that we call corresponding are equal. So the two angles on the same side here are going to be the same. Note this also works on the opposite side, so this bigger angle here on the left and this bigger angle here on the left are also corresponding and are equal. Another way to visualize this is just take this little part of the triangle here and just slide it up along the sloped line. You can see that these would be the same. All right, well, when two parallel lines intersected by a diagonal line are shown, alternate interior angles are also equal. So interior angles, meaning on the inside of the two lines, and alternate because they're on opposite sides. And one thing you can kind of think of here, at least the way I've learned this, I don't know what color is going to work best here, is there's kind of this Z effect. So notice, like, if you trace this out, you will, sorry, it's hard to align my cursor right now. If you trace this out, you get the Z shape. So the angles inside of the Z are going to be equal. Those are the alternate interior angles. Note this also works with the Z the other way, which is kind of weird looking. So if we take a look at this with this kind of a Z shape, okay, so this Z here, these alternate interior angles are also going to be equal. So by definition, if they're alternate interior angles, they will be equal to one another, regardless of what side of the shape they are on. Okay, one more of these situations here. You could also have alternate exterior angles. So here, same situation, but now we're looking at the exterior. These alternate ones are also equal. And again, that also works for the bigger angle here on the top left and the bottom right. Those two will also be equal. Okay, now let's look at angles that happen to be supplementary. Whenever we say a supplementary angle, that means they work together to add up to 180 degrees. So we'll look at several examples of situations where our angles add up to 180. The first is when you have the sum of two adjacent angles on one side of a straight line. So we have the straight line from A to C, and another one cutting through it. Well, the angles on either side will add up to 180 degrees always. No matter what this line BD is pointed toward, it will always be a total of 180 if you add them up. Okay, well, let's also look back at our previous discussion where we had two parallel lines that are intersected by a diagonal line. We're not looking at alternate angles anymore. We're looking at same side angles. So the angles that are on the interior on the same side will add up to 180 degrees. And this works on the other side as well. Very similarly, the same side exterior angles will do the same. These will also add up to 180 degrees. So you can see the example at the top here. Our exterior angles on the same side will add up to 180. Our last situation is when you look at a triangle. Every triangle, no matter what way, no matter how it's shaped, no matter how it's oriented, regardless of any situation you have, as long as it's a triangle, the three angles on the inside will always add up to 180 degrees. So in this case, the angles lowercase a, b, and d will add up to 180. We're going to look at one more case. This is a very specific case. I don't have a special name for it, so I just called it a special case, This is a situation that we encounter quite often in physics, maybe several weeks at least into the semester. So we won't see this for a while, but it is something we will see. So on the right, we see something that occurs whenever we have an inclined plane. So something that's moving along a ramp, for example. So here we have two angles that are defined. Theta, which is the angle here on the left, and phi, here between the line C and the arrow F. So these are two angles, and notice that each angle is perpendicular to sides of the other angle. So here, this line moving along A is perpendicular to this line F. And the top line here, B, is perpendicular to the line C. Anytime you have this situation where both sides of your angles are perpendicular to one another, the two angles, theta and phi, will be equal to one another. Now this might seem a little weird or hard to visualize at first, so let's try to put some numbers in and try to make sense of this. So let's just pick some random numbers. Let's just say theta is, 30 degrees. Okay, so if theta is 30 degrees, well, we should know something else. Remember, triangles add up to 180 degrees. Well, this is 30 degrees. And because this is perpendicular, this is 90 degrees, this little box here. This indicates a 90-degree angle. So we have 90 and 30, that adds up to 120, which means if the total is supposed to be 180, this guy right here has to be 60 degrees. Right? I keep screwing up my cursor. Because we know the total, what is going on here? The total in a triangle has to be 180 degrees, so 90 plus 30 is 120, plus 60 is 180. Okay, well, so far so good. Now recognize that this here is also a right angle. So this is also a 90-degree angle. So if this is 60 degrees, together these have to add up to 90, so this must then be 30 degrees. So what I've just done is basically show you the proof that those two angles are the same. We can use our rule for triangles that these add up to 180 to figure out that this is 60, and then knowing this is a right angle, in other words 90 degrees, helps us figure out that that is 30 degrees. Okay, so be aware that anytime you have a situation like this, those two angles are the same. Okay. Let's move on to the beginning of our final topic in this lecture. We're going to deal with right triangles quite frequently in the course. So a right triangle, by definition, is any triangle that contains a 90-degree angle. And again, we represent a 90-degree angle with this little box in the angle. The longest side of your triangle is always opposite to the right angle. In this case, it would be side C. And the longest side of a triangle is what we call the hypotenuse. If you happen to know two sides of a triangle, any two sides, you can figure out the length of the third side using the commonly known Pythagorean theorem. So, if you again know two sides and want to know the third, use the Pythagorean theorem that is defined as a squared plus b squared equals c squared, where a and b are the sides of the triangle and c is the hypotenuse. But maybe you don't always know two sides of your triangle. Maybe you only know one, for example. So in that case, how would you be able to figure out the other lengths of your triangle if you only know one? In other words, the Pythagorean theorem no longer applies. Well, in comes the trigonometric functions, sine, cosine, and tangent. We won't go into depth with trig identities or anything crazy. All I ask of my students is to know these three trig functions and when to use them. I do give a formula sheet to my students, but I will not put these on there. You need to know these. So, when you know just the length of one side and an angle inside of your triangle, you can use these trigonometric functions to solve for other sides, or you can use them to solve for an angle within. So by definition, we're going to use the abbreviation SOHCAHTOA. Other people have other mnemonics or like ways to memorize this, but SOHCAHTOA is the way I learned it. SOHCAHTOA. So what does all of this mean? Well, first of all, recognize that when we're using the symbols H, O, and A, we're not talking about like housing things. This is hypotenuse for H, O for the opposite side of the angle, and A for the adjacent side, the side next to the angle. So when we say SOHCAHTOA, SOH stands for sine is opposite over hypotenuse, which you see here. Sine of theta is opposite over hypotenuse. Cosine, C, is equal to adjacent A over hypotenuse H. And tangent, T, is equal to opposite O over adjacent A. So the easiest way I think to memorize these three equations is just SOHCAHTOA. In fact, a lot of times students will hand in homework and I'll see this SOHCAHTOA just written at the top of their page or something, just because it's so easy to remember if you know this. Well, that's great, but you can also use trig functions to work backwards and figure out an angle. So maybe we actually do still know two sides of our triangle, and we want to know what the angle inside is. So for example, we could use an inverse of one of these functions. We won't go into details about exactly what all that means, but just know that your calculators do have an inverse function. You'll see like tan minus 1, sine minus 1, cosine minus 1. Those are inverse trig functions. So if we wanted to figure out this angle theta and say we knew the opposite and adjacent sides, we could use this equation to solve. So let's conclude this lecture with two examples working with trigonometric functions. Let's start with question number 1. This question says, suppose that you need to get a heavy couch into the bed of your truck. The bed of the truck is a height of 1 meter, and the ramp makes an angle of 40 degrees with the ground, as you see on the right. The question asks, how long is the ramp? So let's begin first by defining our sides. So notice this traces out a right triangle. So this is the longest side here, so this is our hypotenuse, H. The side here, the height of the truck, that's opposite to our 40-degree angle, so we'll label that as our O. And this side down here is the adjacent side, A. With this in mind, we can now try to figure out how to solve. We are looking for, in this problem, how long the ramp is. So we're looking for the hypotenuse, the length of this ramp, from the ground up to the top of the truck bed. So we're looking for the hypotenuse, and we know the opposite side is 1 meter. So we know the opposite, we're looking for the hypotenuse, so we need to pick our trig function that has O and H in it. So if you recall, SOHCAHTOA, let me write this at the top. Remember, SOHCAHTOA, T-O-A. Okay, just got rid of the T there. There we go. So we're looking for whatever trig function has the opposite side, what we know, and the side H, what we're looking to find. So remembering this, that will bring us to SOHCAHTOA, S-O-H, or the sine function. So we start there. We'll say sine of theta, theta being our angle, is equal to opposite over hypotenuse. It's hard for me to write straight here, sorry. So we start here. Our goal is to solve for the length of the ramp, or the hypotenuse, so we have to rearrange this equation. To do that, I multiply the h to the other side, so I'll just write that out right now. H times sine of theta is equal to opposite. And now we want h on its own, so we divide the sine to the other side. So we'll be left with our hypotenuse, what we're looking for, is equal to the opposite side divided by the sine of our angle theta. Okay? So at this point, we have rearranged our equation. We can now solve. And again, I mentioned this in our previous lecture, but get used to rearranging your equations first and then plugging your numbers in. That's the common way to solve problems. And so we now have 1 meter as the height on our opposite side, divided by the sine of our angle, which was 40 degrees. So if you plug this into your calculator, 1 divided by the sine of 40 degrees should give you 1.56 meters. Now, you can kind of do a check once you get this result, because you should know the hypotenuse is going to be longer than 1 meter, right? Because the hypotenuse is always the longest side of your triangle. So at the very least, we know our answer should have been over 1 meter. So that's one way we can kind of check if our answer makes sense. Okay, let's then work on number 2. Number 2 says use the information provided to solve for the unknown angle theta. So in this case, on the right-hand side, we have a triangle with the opposite side labeled as 3 and the adjacent side labeled as 4. So we know, again, we know the opposite side and we know the adjacent side. So if we want to solve for the angle, we could do one of two things. If we wanted to take the extra step, we could solve for the hypotenuse, but you don't need to do that. We don't need to know the hypotenuse at all to work out this problem. So instead, recognize that we just need to pick a trig function that has the opposite and adjacent side in it. So going back to SOHCAHTOA, wherever we see the one with opposite and adjacent is the one we want to apply here. So in this case, that's TOA, or tangent. So let's start with our tangent trig function. Tangent of theta, by definition, is equal to opposite over adjacent. We are looking to solve for the angle theta. So to get theta on its own, we take the inverse. So we go to theta is equal to the inverse tangent, tan raised to the minus 1, over opposite, of opposite over adjacent. All right, so anytime you look for an angle, you're going to be using these inverse functions. Well, at this point, all we have to do is plug and solve. So we have tangent minus 1 of the opposite side, which was 3, there's no units here, and the adjacent side, which was 4. So you just plug this into your calculator, the inverse tangent of 3 divided by 4, and we should get 36.9 degrees. And that is our solution. Notice one thing to make a note of is these inverse functions are sometimes written as arctangent, for example. So sometimes you might see this written as atan. So atan is the same thing as tan minus 1. These are both telling you the same thing. Arctangent or inverse tangent, they imply the same thing. Let me just erase those so it doesn't look confusing. Okay, so with that, I think that's a good point to conclude our math review. From here, we're going to hop into the actual physics material. It's going to be kind of a segue, though. We're going to start with significant figures and scientific notation before we actually start talking about things like position, velocity, and acceleration. Until then, take care and have a fantastic day.